Alrighty, okay. So let me go back a little bit just to sort of get us back to maybe a somewhat familiar point so I can get us on the frame of discussion for what we're talking about. So tonight, what I really want to do is I want to sort of finish out my, I guess, background discussion on all of the stuff in AASHTO 610. In other words, you know, I've been throwing some terms out at you over the past little lecture. Like I threw out what is MP versus what is MY, and I think later on last time we started to talk about D sub C, the depth of the web and compression and things like that. I'm trying to go back and explain a lot of this stuff before we dive into the spec. If we just started diving into the specification right now, specifically section 610, looking at the resistance, I'd have to backtrack so many times that we'd sort of lose touch with what we were talking about. So I need to sort of go back and explain some of these fundamental concepts. So some of this stuff might be new. Some of it might be familiar from stuff that you've seen in undergrad steel design or what have you. But it's all, the whole purpose is to get us speaking the same language when we look at the spec later. Okay, so let's go back to some of the stuff we talked about last time. We looked at the maximum capacity. We started off, let's look at the maximum flexural capacity of just a steel beam by itself. And we recognize that we have a term for that. We call it MP, the plastic moment capacity, Fy times Zx. You know, find the point where the compression equals tension, find that. Find moment arms, some moments. There you go. Sound good, right? Same story with reinforced concrete design. That's a very common philosophy if you're doing an analysis of a cross-section to determine its flexural capacity. Some moments, you know, about the point where compression equals tension. Same story if you're dealing with both materials together. When we look at a composite beam, we do the same thing. Because the geometry is a little funky, there's a number different cases. Luckily, the spec derives all that for us, and that's where all the stuff in Appendix D came into play. So we used this last time, just sort of go down the line. Keep in mind that for positive bending, we neglect the rebar. For negative bending, we neglect the slab. All right? Sound good? Okay. Now, we also recognize that the yield moment ain't quite as simple as it used to be. It used to be just Fy times the section module. So I could look up a section modulus in the steel manual, multiply it by Fy, and there you go. In composite construction, that's not so direct. It's not so straightforward. Specifically because we have to recognize that idea of staged construction. Those loads are going to progress through the section as the girder becomes a bridge. You know, the steel beam by itself has got to resist its own self-weight, the weight of all the cross frames, the forms, the studs, the stiffeners, all that, and the weight of the wet concrete. But once the wet concrete cures and becomes composite, well, then that section together can resist, you know, the remaining dead loads. It can resist the live loads. So computing something like the yield moment is also not as straightforward. We have to first determine that additional moment that will cause the stresses to reach Fy, and then add those moments up to get the yield moment. And keep in mind you can have a yield moment for the top flange and for the bottom flange. And that's where we ended off last time, right? Something right like that? I think we might have briefly mentioned this. I don't want to go into calculations with this D sub C yet because I want to get to that when we can actually utilize it, you know, for determining capacity, and we got to talk about some stuff before we get there. So, you know, sort of bear with me. I got a lot of material I'm going to throw at you, but it'll make sense as we progress. Okay, so D sub C. D sub C is a term that shows up quite a bit in the spec, and it's the depth of the web in compression. D sub CP is how much web is in compression at the plastic moment. So, to give you kind of an idea, in our last example, we computed MP, and we found that the plastic neutral axis was in the slab, right? Isn't that what we found on that example, that it was in the slab? Well, that means that the plastic neutral axis is in the slab. Everything above that line is in compression. Everything below it is in tension. So for that girder, all of the web was experiencing tension in MP. So how much of the web is in compression at MP, DCP? It's 0. Does that make sense? Oh, it's been a while probably since you looked at that, but I'm just sort of, trying to get the memory banks jogging and whatnot. Now, this D sub C is going to become pretty important to us when we start looking at stability of I girders. Local flange buckling, particularly lateral torsional buckling, because as you all know, we have a part of the beam in compression, and things in compression like to do this thing called buckling. So there's a lot of, background that we've got to discuss there, and I'm going to throw the term D sub C at you quite a bit. D sub C is the depth of the web in compression, okay? And just like, anything with bridge engineering, sometimes it's not quite as straightforward. If you're dealing with a non-composite shape, it's just where the centroid is. It's pretty simple. But with a composite shape undergoing staged construction, you just got to be careful with computing DC. Luckily, the spec helps us out pretty bit. There's some nice plug-and-chug formulas that we can use if we're looking at the elastic range and we're looking at positive bending. Nice, pretty plug-and-chug formula. And some more, this is for the elastic range and negative bending. And then there's some more language in the spec. I don't want to get too heavy into this. I've provided you the important stuff, but I really want to sort of tackle the big topics tonight. And then this is for the plastic range, D sub CP. In many cases, again, it's 0. And then also for negative bending. Okay. This is, I think, what I was mentioning earlier, the idea that if you've got a non-composite shape, you don't even have to do all this. It's just where the centroid is. Okay. Everybody okay with this? Okay. Now, I'm going to start, again, like I said, I'm going to start throwing these terms at you one at a time, and I'm going to explain what they are. Okay, so the next term I want to talk about is this idea of a hybrid girder factor. Now, to start, what I mean by a hybrid girder is a girder that utilizes different grades of steel for different components. For instance, an example of a hybrid girder might utilize 50 KSI for the top flange, 50 KSI for the web, and then it might utilize 70 KSI for the bottom flange. Might use a higher grade of steel for the bottom flange. And that's a common practice in other fields of engineering as well. Have you all ever heard of a glue lam beam? Anybody ever heard of that? Where you have strips of timber glued and laminated together to create a beam. Have y'all ever seen those before? Well, if you do, go to like a ski lodge or a church or somewhere like that. They tend to use it in places like that quite a bit. When we design those types of beams, we usually like to take the best species of woods, the ones with the most advantageous properties, and put them on the top and bottom. And for lack of a better term, the trash wood, I don't really want to say it's trash because it is an engineered product, but the lower grades of wood we put in the middle, because the middle isn't really seeing the high bending stresses. Sigma equals my over I, the highest bending stresses are on the top and bottom. So put your best wood on the top and bottom. The same thing's true with a composite plate girder or an I-beam. We can put a higher grade of steel on either the top flange or the bottom flange than we would the web. Makes sense if it's going to see larger stresses to put a higher grade of steel on there. And in many cases, it can be cost competitive. There are some tricky aspects to hybrid girders. If you have a hybrid girder and you put a higher grade of steel on the top flange or the bottom flange, you can make that top flange or bottom flange smaller. Better steel, don't need as much of it. Make sense? Now, if you do that, what happens to your moment of inertia? Well, if you use less steel, your moment of inertia goes down, right? You're making a smaller beam. Well, if your moment of inertia goes down, what happens to the deflections? They get larger. And so sometimes it's a trade-off, and you got to sort of, you got to sort of make sure you know what you're doing and make sure that you're specifying a girder that makes sense. I mean, hybrid girders are very economical in pretty large span ranges and should be considered. I think a lot of times engineers just sort of say the heck with it, and they really don't investigate it very much. But it can be pretty cost competitive. It's just worth checking out. Now, one of the issues with a hybrid girder is the way that it yields. Okay, So let's say I've got a beam here, and I've got the flanges and the webs shaded somewhat differently to sort of indicate. Let's say I've got, I don't know, 70 KSI steel for the flanges and 50 KSI steel for the webs. Well, what happens is I can't really reach the full yield moment, okay, just from a mechanics perspective. Because let's say I hit 70 KSI right here on the top flange. Well, I've already blown through a little bit of the web and yielding right here. Does that make sense? I've already lost a little bit of that capacity. So instead of reaching the full yield moment, we can only reach this reduced portion of the yield moment because some of the web has already yielded, okay? So I propose to you that the ratio of that reduced yield moment to the full yield moment is what we call a hybrid Girder factor. The idea that you can't reach the full MY, so you've got to calculate MY and then reduce it a little bit. And that's where a hybrid Girder factor comes into play. Now I'm going to walk you through the derivation. There's, it's a little involved, but I think it's pretty straightforward too. To make this derivation, I'm going to make a few assumptions. Okay. First off, just to keep this simple, I'm going to assume the section is doubly symmetric. So right off the bat, there is going to be a little bit of error associated with using this in real life. All in all, though, again, it's one of those close enough for government work kind of things. I'm going to assume that both flanges have a yield stress of F sub y for the flange, and the web has its own yield stress. So the whole point is looking at a girder with two different yield stresses. So the flange has F sub yf, the web has F sub yw. All right. The flange thickness is small when compared to the web depth. So when we do our moment arms and distances, I'm going to assume that that flange thickness is 0, and it's going to make my life a lot easier here in a second. And the goal is to try and compute this reduced yield moment. Now, there's a lot going on this slide, so let me sort of explain what's going on. So I propose that if I look at this reduced yield moment, let me go back to this right here. I propose that this reduced yield moment is a function of three quantities. It's the moment that I'm getting in the flanges, it's the moment I'm getting in the web, but then I have to subtract out whatever part of the web that has yielded. Does that make sense? So I propose that to calculate that reduced yield moment, it's this flange moment M sub 1, this yielded, or this full web moment M sub 2, and then I got to subtract out whatever has yielded in the web. So far, so good? Okay. Let's take each of these one at a time. Okay? So, I propose that the reduced moment is going to be a sum of those. To simplify this derivation before I get into this, I'm going to introduce the following terms. I'm going to introduce this term rho, which is the ratio of the yield stresses, and I'm going to introduce this term beta, which is a ratio of the areas, the area of the web and the area of the flange. Sound good? Okay. Let's start off with the first moment, this flange moment. Okay? So the flange force and the moment arm. So what's the moment arm? Well, from the centroid to here, I propose that's half the depth, just d over 2. Sound good? The force, what's the force? Well, I'm talking, at yielding, I propose it's the yield stress times the area. So Fy times the area. Sound good? So that moment arm, F1D1, F1 times that distance, is going to be FYAF times d over 2. Sound good? Now, this is going to sound a little strange. I've got Fy df over 2, so half of this. Would you agree that half of this equals 12/24ths of this? Do you agree with that? You might go, why the heck am I putting this over 24? It'll make sense here in a second because that 24 is going to factor out and they're all going to be the same. So just bear with me. All right. Sound good? All right. Now let's look at this second component, this M2. All right. Force times distance. Well, what's the distance? This is a triangle. Y'all remember where the centroid of a triangle is? 2/3 up. Remember that? All right. So that centroidal distance is 2/3 of this, which is d over 2. So I get that d over 3. Sound good? Now what's the force? Well, it's a triangle, so 1/2 base times height, right? So 1/2 of the stress times the height, which in this case I'm looking at the area of that web, so the half of the area of that web, plug and chug, and I get this, okay? Now, see this blue term here, this area of the web, and then I'm turning that into beta times area of the flange. That comes from those terms that I introduced earlier, okay? I'm doing that because it's going to make my life a little easier as I start to combine all these. I mean, look what's happening. All right, see how I've got this? I plug that in, and now I've got that 24 again. See how I've got this in this format? FYF, AFD over 24 times the quantity. Same thing what I got here. I'm doing that for a reason. Okay, so far so good? Now, I'm ultimately going to have to subtract this part out. And this one's a little more involved. Okay, it's still a triangle, so I've still got that 2/3 component. But now I've got this D prime, and I've got to sort of figure this out. So let's start off with the area. So it's 1/2 base times height, so it's 1/2 of, this base, which is going to be the difference of those yield stresses, because remember that's that component that's yielded. And that height, well, it's the area of the web over 2, but then I got to adjust that by this ratio, this D prime over D, since I've only yielded a certain portion of it, haven't yielded the whole thing. All right. Now I can calculate that distance using similar triangles, saying this is to that as this is to that. I can use similar triangles, do a little bit of plug and chug, and exploit that out a little bit. So that similar triangle relationship, I can simplify that pretty easily by utilizing that row ratio I specified earlier, and I get this. Plug and chug that back in, go through and do all the algebra, substitute this ratio with 1 minus rho, substitute this with beta A sub f, do all the factoring, all the grunt work. You all are, have, reasonably accurate mathematical skills. You all can do factoring and foiling and all that. You know where I'm going with this. So here's f sub 3, here's d sub 3. Multiply the two, and if you notice, see this right here and right here, there's that 24 again. So see where that 24 is coming into play? Okay. So here's the 3 components. Add those up. I propose to you that what's going on in that box down below, that's the reduced yield moment. Okay? Now that's the reduced yield moment. I've got to get the full yield moment, which that's simple because the full yield moment was just this plus that. The whole problem was I had that m sub 3. So do this plus this. I've already derived all of that. Divide the 2, and there's my hybrid Girder factor. Little involved on the algebra, but all in all, I don't think it's a fairly complicated idea. Sound good? If you open up the spec directly, there's your equation. All right? In fact, speaking of, I believe I gave you all a copy of 610 today, right? All right, we will spend a fair amount of time investigating this document, but if you go into that document, specifically, 610.1.10, I want to say it's about like 10 pages into that big pile of junk I gave you all. Let me find this. Ooh. So here's the spec. Let's see. Here's my hybrid Girder factor. I'm on page 6-115, and you notice here's the hybrid Girder factor. So 6-115. Everybody see where that came from? Okay. It goes through and defines beta and defines rho. The definitions are a tad different than what I proposed earlier, but that's trying to handle single symmetry and all the other issues that we kind of assumed. And all in all, this works pretty well. Let me pull something up real quick. I posted this on MU Online. Did anybody see this on MU Online? It should be there. This is a pretty straightforward example. I think when this is all said and done, if all that algebra scared you, I think you're about to see that this is pretty simple. Okay? So I'm going to show you how to compute a hybrid Girder factor for a given girder, and you'll see it's pretty simple. So I propose, okay, so I've got this I-beam. I've got an 18 by 1 inch top flange. I've got a web that's 40 by 1/2, and I've got a bottom flange that's 18 by 3/4. Okay? Now, everything's 50 KSI except for this bottom flange, which is 70. And I've got it sort of shaded in. Sound good? Now, I propose to you, and this is something to keep in mind, you can go through all the math and still get a hybrid Girder factor of 1, even if you've got, a hybrid section and you're using different grades of steel. Just because you're using different grades of steel does not dictate that your hybrid girder factor will equal 1 or be less than 1. The only time it's less than 1 is when you can guarantee that you've yielded some of this web. Let me show you how this works. Now, I'm looking at these grades of steel, and I guess right off the bat that I'm going to reach 50 KSI up here before I reach 70 KSI down here. Reasonable guess? Let's see if it's an accurate guess. All right? So I have an I-beam with these dimensions. We should by now be able to compute the moment of inertia of that. We should be good. Sound good? And we should also be able to compute the section modulus of the top and bottom. I've got the centroid and everything listed here. Should be good. Everybody all right? Okay. So I'm going to start walking you through some of these terms. Okay, to start off, D sub n. D sub n is the longest distance from the centroid to one of these flanges. Now I propose if here's the centroid, which you all can go into Excel and compute this, from here to here is about 22.574 inches. From here to here, it's 19.171. So I propose it's the largest distance. You know, this is going to be the largest distance, and I'm going from here to the edge of that flange. So I've got to take that flange thickness off, and that's where I get this. Okay? Sound good? All right. Now, once I figure out what direction that is, either up or down, since this is my hybrid girder, it stands to reason, or this is my hybrid plate, stands to reason I'm going down in this direction. Once I figure out which direction that is, this A sub Fn, it's the area of that flange. So if this is the longer distance, it's that area. If this is the longer distance, it's that area. Sound good? That's A sub Fn. Now, this stress value, this F sub n, like I said, I'm going to take a wild guess and say that the top flange hits 50 KSI before the bottom flange hits 70. And what I mean by that, well, if I've got 50 KSI at the top flange and the section modulus to that top flange is 816, that's what I get up here from my Excel calcs, I propose that it takes about 40,000 inch kips of moment to get that stress. Sound good? Now, if I take that moment and then say, well, how much stress did that cause down here? It caused about 58.86 KSI. Is that a reasonable calc? That's not very difficult, right? Okay. So I propose this F sub n, that's that stress on that bottom flange at 58.86. Once you get that, the hybrid girder factor is very plug and chug. Calculate beta. I've got D sub n. I've got the web thickness. It's a 1/2 inch. Got the area of that flange towards that longer distance. I get 1.61, 1.616, something like that. Calculate rho, plug and chug, and there's my hybrid girder factor. So I propose that I can't use all the yield moment of this girder. I can only use, 99.3%. Sound good? Now, if you do this exactly and go through and actually integrate the stress profile and do all the math, you do it exact, and you're trying to account for those assumptions that were, made, you get a value of 98.8%, so a tad lower. Close enough for government work. Sound good? Any questions? Now keep in mind, if you're not dealing with a hybrid girder, if it's all homogeneous, it's all the same grade, RH is 1. And you can go through the math and see that that'll come out to be that way, but RH is 1. And that tends to be the case with a lot of these factors. In most cases, they're 1, but in the cases that they're not, I want you to at least have an understanding of how to compute those. Everybody good? Okay. All right. Like I said, I know tonight might seem like a hodgepodge of a bunch of different topics, but I wanted to at least get you familiar with what's coming. Okay, let's talk a little bit about 610. Okay, so 610 is the big document, the big set of specs that you all got tonight. And by and large, this is the document which governs how we compute the capacity of an I-shaped steel beam. In other words, this is the document by which all the designs that we're about to do in this class, your design project, any design that you do when you get out of here, this is how an I section is sized. How big does this flange need to be? How big does this flange need to be? How thick does this web need to be? So on and so forth. All right. What I'm going to do is talk about or try and get through some of the red sections tonight, or at least go through them as much as I can. The blue sections are the stuff I'm going to hit up later or try and discuss later. So later we will talk about constructability. Later we'll talk about fatigue. But I'm going to try and talk about just in general. We've already seen some of the stuff in general tonight because we looked at the hybrid girder factor. I'm going to try and talk a little bit about cross-section proportion limits, the service limit state, the strength limit state. Later, we will talk about shear. Later, we will talk about shear studs. I don't like that name, shear connectors. I'll hardly ever use that. I'll call them shear studs. You might have heard the term Nelson studs if you are in the bridge industry, so it's all kind of the same. We'll talk about 6'10", and 6'10", which is all bending strength as well. Now, there are a number of appendices that pertain to 6'10". We've already dealt with one of them. We've already looked at Appendix D. I gave you all Appendix A tonight. I don't have a copy of Appendix C for you, but I might show you. Appendix C is just a bunch of flow charts. And Appendix B, if we have time, we'll talk about that. That is an involved topic, moment redistribution. If we have time, we'll talk about it. Okay. Sound good? All right. Now, I want to make sure that you're understanding the anatomy of the document that you're looking at. So 6'10" is broken up into various sections. We got 6'10", 1, 6'10", 2, 6'10", 3, so on and so forth. 6'10", 1 is just sort of the overall, hey, here it is. So, you know, where do we find all this, the stuff in the spec on using steel sections or short-term composite or long-term composite? We've already defined what all that stuff meant. Now we know what it means, okay? We needed to talk about that stuff first. Now that we understand it, we can get through it. There's other various parameters specified in 6'10", hybrid girder factors, web bend buckling. We're going to talk about that tonight, and some other stuff. Let me actually pull that up. So let me pull that up since everybody has this. There's this. Okay. So the handout that I gave you all tonight started, you know, like right here. It should say I-section flexural members. That's what you all have tonight, right? All right. If you go to the next page, you know, and actually look in the language of the document, I mean, this stuff should seem pretty familiar, even though you haven't even read it. For instance, I'm looking at this sequence of loading provisions, 6, 10, 1, 1, 1, 8. The elastic stress at any location on the composite section due to the applied load shall be the sum of the stresses caused by the loads applied separately to the steel section, short-term composite, long-term composite. While we haven't seen this in the spec, it's there, you know. This is the stuff we've seen before. Sound good? So this stuff should be somewhat familiar. It's just sort of the overall general provisions. The hey, here it is for steel girders. You know, modular ratios. You know, what's a reasonable modular ratio? What have we been using this whole semester? N equals 8, you know. Where do we get that? We get that for KSI concrete. Pretty reasonable value. Sound good? All right. What else? We've got some other provisions on variable web depth members and some stuff we might talk a little bit about later. This stuff on flange stresses, we will get into that, but we'll talk about it later. I don't even want to get into lateral flange bending without explaining what it is. Minimum deck reinforcement, how much rebar we put in the top of the section. Remember we said we were going to put, what, 1%? You know, the 2/3 and the 1/3 layer, that's right here, 6'10", 1/7. Web bend buckling resistance, we will talk about that a little bit later, and so on and so forth. Okay. So far, so good? All right. Now, I do want to investigate this section pretty in depth with, because this one's pretty simple. Section 610.2 is highlights a series of cross-section proportion limits. And by and large, there's two big reasons for it, but let me explain where it comes from. Okay? You all are engineers who are going to be sizing an I-beam. You're going to be saying, use an 18-inch wide flange and so on and so forth, right? Well, here's the problem, okay? You all could come up with flange geometries and web depths and stuff all over the place. okay, that you might use the spec and you might get capacities that look great. But you have to keep in mind these specifications were written for a particular type of behavior and a particular type of girder. Let me give you for instance. All right. Let's do it like this. Would you agree, I know this is going to sound silly, but would you agree that this is an I-beam? Okay. Now let me ask you this. Is that an I-beam? I mean, is it? I would argue that this does not behave like an I-beam. It behaves more like a T-section. The equations and the models that are specified in this document are assuming a particular type of behavior. If you just start going willy-nilly and sizing girders that fall outside these boundaries, then the equations you're using aren't going to make any sense. So what's going on in this section 610.2 is trying to ensure that the girders you're sizing actually fall within the spec. Okay, that's one reason. Another reason is fabrication. Okay, so let me just sort of stop going on about the slide, actually get into the spec. So I want everybody to follow along with me on this one. So I'm on, in that handout I just gave you, I'm on 6-120, and I'm at section 6.10.2. So it should start off looking something about like this. So far so good? Okay, all right. So first off, web proportion limits, okay? The first limit says that the web slenderness, the depth over the thickness, shall be less than or equal to 150 anytime you don't have a longitudinal stiffener. Now what's a longitudinal stiffener? That's when your web gets so thin and so slender that you decide, I got to have an additional stiffening element right there running along the beam. Unless you can avoid it, don't use a longitudinal stiffener. It's just another plate you've got to throw on the section, another massive amount of welding, another massive amount of fabrication, which means it's going to hit your wallet a lot harder. When possible, avoid that. Now, if you've got some, Star City Bridge or, Nitro to St. Albans Bridge where the girder's 12 foot deep, you might not be able to avoid it. But on a creek crossing or something, don't ever put a little longitudinal stiffener like that. It's just a waste of time and money. All right. Bless you. Okay. So that's just ensuring that the webs don't get too slender for handling and buckling and things like that. Okay. Flange proportions. Okay. One of the big ones is this one right here. The idea that the ratio of the width and thickness of the flange, we do BF over 2TF because we're only looking at, this much of the flange. So here's the flange. Here's that. We're only looking at, this much. So that width is BF over 2, and that's TF, right? What happens if this thing gets too slender, or this slenderness gets too large? Well, if you're dealing with a plate girder, how do you fabricate a plate girder? You take a plate and another plate and you weld them together. What are you doing when you're welding? You're heating it up to a very excessive amount. If you have a really flimsy plate and you heat it up really hot, what's going to happen to that plate? It'll warp, it'll distort under that heat. This limit is to ensure that you don't get too much excessive distortion under the welding process. Now our flanges should not be approaching that anyways, because as you'll see later, that's not a very economical design. This next one, for instance, it has a different reason. You get really nice moment rotation characteristics when you meet that limit, and that's good for economic designs, as we'll see later. And I'm not going to go through every one of them. For instance, this one here, this 0.1 IYC, IYT over 10, that's trying to guard against sections that look like this. In other words, you can't have one flange disproportionately larger than another. In other words, it's not an I-beam, it's a T-shape, and the equations don't make sense. Okay? So this IYC or IYT, it's the moment of inertia of the flange this way. So it would be the thickness times the base cubed over 12. And whether you take this divided by that or that divided by this, it doesn't really matter. That's why the limit is either 1/10 or 10. So as long as you meet that comparison, you're good. Again, just trying to ensure that you're actually dealing with an I shape. Okay. Any questions? Okay. All right. Any questions on that? One of the first checks we can make is to look at 610.4, which is the service limit state. Now, this is pretty straightforward. All it's saying is, if we're looking at the permanent check, the 610.4.2, all this is saying, long and short of it, is that the stresses in your bottom flange and in your top flange shouldn't exceed 95% of Fy at the service level, okay? That's, in other words, just taking the raw loads and adding them up directly. Now, when we look at strength limit states, that's where we're actually factoring, the 1.25 times DC, the 1.75 times live load, et cetera. That's when we're using ultimate loads and ultimate capacities. This is just to ensure we don't get, this service limit state check is just to ensure that we don't get too much permanent deformation. And I don't really have much to say about it because when you all come back in a couple weeks and we do this, for example, the example we've been working on in class, you'll see this is a really easy check to do. There's really not much to say. It's just M divided by S, M divided by S, M divided by S. Just add it up and see if it's less than or equal to 95% of Fy. That's it. It's really not much to it. All right. So far, so good? Okay. Now, when you get into 610.6, okay, as I said before, the big thing you have to differentiate is whether or not you're dealing with a beam or whether or not you're dealing with a plate girder. If you're dealing with a beam, 610.6 is going to refer you to another section of the spec, specifically Appendix A. And I gave you all Appendix A tonight, didn't I? Okay. Appendix A is dealing with more stocky, I would say, I shapes. If you've got a really, really slender I shape, you're going to go to 610.8. In other words, the more slender an I-beam gets, by and large, the weaker it is. Okay? The more stocky and compact it is, the more capacity it's going to be able to take. Okay? And before we start, really digging into this, we got to take some time and go into the theory. Now, some of this stuff you might have seen before, but we need to make sure we're all speaking the same language. So let's start off with some basic beam stuff. Now, I've been making a blanket assumption this semester that everybody in here has had an undergraduate course in steel design, and I'm hoping that is the case. If not, this might be brand new. If you have had steel, this is probably going to be old hat. So let's start talking a little bit about lateral bracing. Okay? Now, a beam, like a column, presents a stability issue. Okay? I have a portion of that beam that's in compression, and things in compression like to buckle. Okay? Now, another thing, like columns, the longer a column gets, the weaker it gets, right? Because the longer a column gets, the more slender it gets, the lower its buckling capacity is. And you all have had strength of materials or mechanics of deformable bodies, whatever you want to call it. So you all have seen this stuff before, am I correct? Okay, all right. Now, for beams, what we're more interested in is the distance between bracing elements or between cross frames. And we call this distance the unbraced length. Now, here's what I mean by bracing, okay? One particular type of bracing is a slab. If you have a composite girder system, like the stuff we do in this class, when you're looking at the strength limit state of the bridge intact, LB is 0 because the flange is fully braced. Make sense? Now, some other common options are, well, maybe you've got beams or elements framing into a given segment, like beams in a floor system. So, for instance, if I'm looking at this particular girder, these floor beams are framing into that girder and serving to brace it from going side to side. Make sense? In bridges, a very common example is a cross frame. Maybe something about like this, right? Make sense? Okay. Why is that important? Well, it's important because of this. It's important because of lateral torsional buckling. Now, I like movies, so I'm going to show y'all something real quick. I have here a lateral torsional buckling test. It's only 2 minutes long, so it's not that big of a deal. Now, this is on an aluminum beam. It's not a steel beam, but in the end, the phenomenon is the same. So let me go ahead and load this up. See if the sound works.
This video shows a plate girder being tested under bending. The material used in the test is an aluminium alloy. The web has shear stiffness to prevent it from buckling.
Let me turn this up a little bit. Let's turn it all the way up. Live dangerously.
The test is an aluminium alloy. The web has shear stiffness to prevent it from buckling. The loading diagram shows the beam being subjected to 4-point bending. It is also laterally restrained, but close to the ends, leaving a large, laterally unrestrained length. The testing rig is now starting to apply a pair of equal vertical loads to the central third of the beam. As the loading is applied, the beam begins to sag. Under this loading arrangement, the bending moment is uniform in the middle third of the beam. Now, as the beam is loaded, the top half of the cross-section, which is in compression, starts to buckle sideways. However, movement is restricted by the bottom half of the cross-section, which in fact is in tension. The overall effect is to cause the middle of the beam to twist over, as well as move sideways. The beam eventually fails by local buckling in the flange, which is induced by the lateral torsional buckling deformation. The graph shows an initial linear relationship between the applied force and the vertical displacement.
Did everybody see how the beam was sort of kicking out and twisting like that? Okay. That's a phenomenon known as lateral torsional buckling, and it's one of the biggest phenomenons that we in steel design need to deal with when we're designing beams. Okay? All right. So, if you have a beam and you apply a moment to it, as particularly a steel I shape, ultimately what it will want to do is kick out and twist. You all saw a video of that. Here's a couple images of it. Ironically, the image on the right was a test that was done in Purdue in the mid-90s on some stuff for the ASHTO spec. This was particularly to try and push the inelastic envelope, and a lot of stuff that was done on this test ended up in Appendix B. So just food for thought. So now, I know you all love math. You're engineers, so I know you can't get enough math. Although, that being said, if you're not a fan of calculus and differential equations, I'm sorry, we're going to have a little bit of that. But bear with me, we will get through it together. Everybody believe that? Okay. All right. So, let's talk a little bit about this lateral torsional buckling because I want you to see where a lot of these equations come from. Okay? Now, when you all took strength of materials, you all did torsion in there. But I can almost guarantee you that you almost exclusively did torsion problems on sections that were circular. Okay? And the reason why is because circular cross-sections don't warp. We're not looking at a circular section, we're looking at an I-beam. It will warp. Okay? So I propose that when you apply a torsion to an I-beam, you get two moments that respond. A moment from warping and a moment from pure torsion. And we're going to take each of these one at a time. Let's start off with the pure torsion. Now, you've seen this stuff before. This is what you did in strength of materials. I have a segment. I take that segment and I apply a torsion. It twists. Okay? How much does it twist? Well, I can relate the amount of moment to the angle of twist. You all probably did that. Angle of rotation is TL over GJ. Remember that? Pretty straightforward. In other words, GJ times the rate of twist, that's your moment. So far, so good? That's simple. That's pretty straight moment. That's just that pure rotation. Okay? That's not the warping effect. What do I mean by warping? Okay? Circular shafts don't warp. And what I mean by that is if I take a section that's circular and I twist it, all it does is rotate. That's it. If I have a shape that's not circular, It doesn't respond like that. In other words, not only does it rotate, but it warps. It deforms in and out of the plane. Now this is sort of an exaggerated view of that, but if I look at an unwarped versus a warped section, the flanges, they actually deform in and out of the page. Does that make sense? Anything that's non-circular will respond like that. That's why when you take an undergraduate course in deformable, you stick with circular sections. And if you're a mechanical engineer and you're designing for torsion, or you're trying to design some element to resist torsion, you're going to want to always use a circular cross-section anyways. So, food for thought. Okay. Now, when you look at an eye shape that's warped, mostly it warps in the flanges. The web doesn't really do a whole lot. So we restrict a lot of our discussion to the flanges. Okay? So we're going to assume that there's no warping in the web, and we'll focus all our attention on the flange. Ultimately, if we can figure out the shear in that flange and figure out a moment arm, we can figure out warping pretty easily. So, if we investigate one of these flanges and say, well, afterwards it's deformed some amount, well, I say, okay, if it's deformed a little bit like this, I've got this angle of twist, I can say, all right, use a little bit of similar triangles, and I can determine that that deformation is h over 2 times that angle. Sound good? Now, just because I like taking derivatives, we're going to take the third derivative of that. Seems reasonable enough, right? I'm sure you're like, what the heck's going on here? You'll see here in a second. All right? So if I take the third derivative of this, I'm treating my angle of rotation as a variable. Everything else is a constant, so that factors out. Everybody okay? Here's why I'm doing that. Okay? This is a very fundamental differential equation that if there's any one differential equation you remember from undergrad, it should be that one, that the second derivative of deflection is m over EI. In other words, once you get your moment, remember you can integrate it twice and there's your deflection. Y'all remember that? Okay, so that is a very fundamental differential equation. This is another one. You might not remember this, but you definitely have used this when you drew shear and moment diagrams. I mean, remember how you draw a moment diagram? You get the shear, you integrate it, a lot to a little, so the moment diagram goes like that. Y'all remember that? Well, I propose that if the second derivative is related to moment, the third derivative is related to shear. So this third derivative, I just took the third derivative just for the sheer heck of it, no pun intended. See, I threw jokes in that I can relate that deflection to the shear. Okay, that's really what I'm trying to do here. Okay, why is that important? Well, that shear force times that distance, sum that, I can get a moment. Take moments, recognizing I've got shear on either side, plug and chug, and I've got this new expression. Everything that's in that set of parentheses is a section property. I mean, I've got the moment of inertia of the flange, the height squared over 2. We have a particular name for that. We call it a warping constant. If I go back to the steel manual, for instance, if I pull up the, your celebration of learning at home, this is some pages out of the steel manual, and if I look over here on the very right, I've got torsional properties. What are the two properties that they list? Pure torsion, warping. So, sound good? And don't worry, warping constants can get huge. 186,000 inches to the 6th. That can happen. Okay. So far, so good? So, right now, I propose that if I wanted to write out the full expression for torsion, I've got pure torsion and warping torsion, and it comes to something like this. And I get lazy with writing my derivatives, so I'm going to say that this first derivative is just phi prime, that's phi triple prime. Everybody okay with that? All right. I'm going to throw a little bit more math at you tonight, and I can tell math's getting to be a bit much. But we're hitting that break point. So what do you say? Take a little break, come back 10 or 15 minutes? We can stay if you'd like. There we go, getting a little bit less. Let's take a little bit of a break. Let's get back together, what, 7:45, something like that? All right.